Hello and welcome back to another LeetCode video. Today we're looking at LeetCode 3347 maximum frequency of an element after performing operations version 2. So we solved version 1 of this problem before, and if you're interested, the number is 3347, and it's exactly the same problem, except now we have different constraints where we now have numbers not up to 10 to the 5th, but up to 10 to the 9th. So in case you don't know the problem, let's just go through it to understand it, and then I'll show you how to solve it effectively. So you're given an integer array of numbers and two integers k and num operations. You must perform an operation, num operation times on nums, where in each operation you select an index I that was not selected in any previous operations. Add an integer in the range of -k to +k to nums at position I. Then we should return the maximum possible frequency of any element in nums after performing the operations. So in other words, we're getting a number array, and we have the ability to change the numerical value of up to num operation different elements in nums, and we can change it by adding and subtracting a value in the range of -k to +k. And the goal is to make an element more frequent and then determine, well, what's the maximum frequency that we can get by making those changes to the array. Okay, so yeah, let's look at an example again. So here you see the numbers 1, 4, 5, and k is 1, meaning we can adjust these numbers by at most -1 or +1, and we can adjust two of these numbers to try to make an element the maximum frequent element in the array, and then return the frequency. So here you can see we can change 1 to 0 and to 2, but 0 and 2 don't exist in here, so we're not changing the frequency of anything by performing these operations on the first element in nums. However, when we pick the second element, which is 4, and we now add 1, and suddenly we have two 5s. So the maximum frequency would be 2 automatically. And if we change it to -2, 3 by subtracting 1, we don't win anything because there's no other 3 in here, so not increase the frequency of anything. And same with the 5, adding 1 doesn't do anything, but subtracting 1 gives us 2 4s. And then again, the maximum frequency would be 2 because we have 2 4s. And that's exactly how this is explained here. They explain that, they get 4, 4, and that's good enough. That's a maximum frequency, and that is returned. Next example, so we have 5, 11, 20, and 20. Now we have the ability to adjust only one value in the array by, well, within the range of -5 to +5. So what can we do? Well, we could adjust this 5 to 10. Doesn't touch 11, so it's not going to change the frequencies that we have. And by the way, the maximum frequency right now is 2 because we have two 2s. So what about 11? Well, we could add 5, then we get 16. We could subtract 5, then we get 6. So changing 11 doesn't do anything as well. Maximum frequency stays 2. Now, if we start to modify the 20, all it does is just reduces the maximum frequency, right? Because 20 can become 15 or 25. And both of them don't exist in the array. And by the way, I could also just subtract 1. So 20 becomes 19. Same result. So here, none of operations do anything. And by the way, in the problem says, we must perform an operation exactly num operation times. But since we can add 0, not changing the array is also possible. Right? So if you find out that only need to change one value effectively, like in this area here, where we change the 4 to 5 or the 5 to 4. The other operation would be just adding 0 to an existing element, that you are sure that you actually perform all the num operations, just in case you were wondering. So yeah, so that's the problem. And now the question is, how do you approach this? Well, a naive approach would be, maybe we count all the frequencies, or we create, I don't know, maybe a hash map of all the frequencies. and then we try to adjust all of the numbers to match any of these frequencies. Obviously, that would be extremely expensive. What would we have to do? Probably have an O of n squared, if not larger runtime, which is prohibitively expensive, when we're dealing with that many numbers. So I've seen other people use dynamic programming approaches, but I think there's a simpler one. And if you've seen the previous video on 3346, you will see that this is exactly the same solution. Luckily, when I built 3346, it was already good enough to also work these stronger requirements. So how do we approach this problem? Well, if we let's go to the drawing board here. If we had, let's say we have a small diagram, and that represents the numbers that we have in our nums array. And in the problem description, it didn't say anywhere that the numbers are sorted, even though the examples that we saw were in sorted order. Now, if we would assume that all elements are in sorted order, I think that would simplify the problem a lot for us. So what we would get is, we would get some kind of non-decreasing sequence of numbers that comes from our nums array, right? So this, the value of nums at index I would also increase when nums is sorted. And now what we could do is we could just look at a specific number in nums at position I, some concrete value for I don't know, maybe 10. And we could look at what value it has, right? Maybe it has the value, I don't know, 20. No value. And if we have a value of k, with k is equal to, let's say 5. So that means that we could potentially, well, if we want to know which numbers in nums we can adjust to match the value 20, well, those are obviously all the values that fall within the range of, let's say, 20 minus k, and of course 20 plus k. Right? So what we would have is, we would have essentially a nice defined range where we can adjust the numbers. I think wait, do it like so. And with, right? So now suddenly we know we could determine, what is this index here? Maybe call this S, and maybe call this index here E for start and for end. Now we suddenly know, okay, all of these numbers in this range between start and end could be adjusted by adding or subtracting a value between minus k and plus k to have exactly the same value as our element at position I with the value 20. So that's the idea that we're going to use. We will iterate over all of the numbers in our sorted nums array, and at every step, we're going to check out, okay, what is the start and the end range from where we could adjust numbers. And so that's kind of like a window size, right? So you could think of this as a sliding window approach. And as we increase our I and we get to different values than 20, we have to, well, we will have a new window, I suppose, that will dynamically adjust to whatever our numbers fall into the adjustable range. Now, that is all good, and that would work if num operations was infinite, but we're limited in the number of operations that we can actually perform. So we might have more numbers that we need to adjust than what we can actually adjust, right? So we need to take the minimum between the size of the window and our num operations to know actually how many numbers in this window are we allowed to adjust. And now, that's the magic thing, if we know that we can adjust a certain number of numbers to have the same frequency as our current value, call this n, that means we can now compute the frequency that we would get for all adjusted values that are now become the same value as n. So what we do is we take the original frequency of n that we have, plus however many elements we now can adjust, given the limitation of number of operations, and that is a candidate for the maximum frequency. As we iterate through the entire array, we always compute the current frequency, and we just remember the maximum as we travel through this array. That is the basic idea. And one thing that I mentioned was we need obviously to compute the frequencies of the numbers before. So we will have to compute a hash map of all the frequencies. We need to sort the numbers array. And then there's another small thing that we need to take care of, and that is if we iterate over the nums array, it's good enough if we just iterate over all of the distinct values in nums, right? Because if we don't do that, if you don't iterate over the distinct values, excuse me, what will happen is we will have a bunch of numbers here that are exactly the same value as n, and that will make it more difficult for us to track exactly, how many of the numbers in the window need to be adjusted. Yeah, so what we will do is we'll not iterate over the numbers array here. We will iterate over the unique sorted set of numbers. But we'll use the numbers array to determine the left and the right boundary for what numbers to include. So that's enough explanations. So let's jump into the implementation. I'm just going to write down the runtime complexity, and we need to sort. So that's going to be O n log n. We need to compute the frequency hash map. That's going to be O of n. And that's all we need. So we're going to have an O n log n time and O of n base. Right. So, and we need to return a result at the very end. That's going to be our maximum frequency. Next, we sort our numbers array. Next, we need to compute the frequencies, and we'll just use a counter. Now we need to determine over which numbers to iterate, and obviously that's going to be a set, right? And we just iterate over them. So we add all the numbers that are in n set. For n in nums. And you will understand in a moment why I'm doing it this way, because we're missing something, but I'll explain that in a bit. So num targets is now a set. So what we need to do now is we have to turn it into a list, right? Probably doing this in more steps than I really need to, but then we also need to sort it. Right, and then we just iterate over the numbers in our num targets array. And well, what should we do? What should be the first thing that we do? Well, we go back to our drawing. How about we compute, we need to compute the min and the max value to determine, what is the range. And then we need to determine the indices of start and end. And we should probably also determine what is our window size, just the difference. So what we'll do is we'll have a min n, right? And that is n minus k. We'll have a max n, that's going to be our n plus k. Now we're going to get our start index. That's just going to use bisect. And that basically finds the first position in the array that is smaller than the value that we're looking for, right? And we're looking for, well, in nums, we're looking for the min value, right? So that makes sure that all indices to the right of start index are going to be larger or equal than min value. And we can do the same thing with the max value, except here we have to bisect the right. What that does is it ensures that all values to the left of the end index are smaller or equal than max n. Right, so now we get the window size. That's just the difference between the end index, the start index. So now we've computed the whole range here, right? Obviously, we're also counting our value n in that range, right? So it's included. And when we compute the max frequency, we need to account for that. And that's what we're going to do next. Now, if the window size is positive, right, then it makes sense for us to check whether we found a new max frequency element. Well, if that is the case, well, we know that the maximum, well, what should we determine? Well, first, determine the maximum operations that we can actually make, right? The green arrows. How many could we, in theory, make? But then we have to limit that by the num operations that we're allowed to make. So let's compute max operations first. That is nothing but the window size minus however many values of n we have in our range between start and end index. Now this is where the frequency comes in. That is why we computed that frequency, and we're just getting that frequency value. So that's the maximum number of operations we can make in that window to get all the values equal, all of the values in the window equal to n. Right. Now, what is the max frequency? The max frequency is, obviously, it's going to be current frequency of n plus how many values we can change in the window to get equal to n. So that's going to be the minimum between max operations and num operations. And now the only thing I have to do now is we have to say result is the maximum between current result and of course max frequency. Right. So that does everything, but we still have a little why here. So if we go back to our drawing board, we've implemented everything now in code that we wanted to implement. Now there is an edge case that might not be so obvious, but that we have to take care of. Let's say, for example, that at I10 there's one number, and that determines that range. And I'm going to pretend that maybe at I11 we have another number. However, the range of that number goes to something this, right? So we would compute now, what's the max frequency that we can get by modifying the elements in the window around whatever at I equals 11 is, and that's good and all. But what now with this range? What do we do with this? We never considered whether we can adjust these upwards, these values, to maybe a value that doesn't exist in the array. That would be here. So this value does not exist in the nums array. However, it has a neighborhood that we could try to adjust to match that value, right? That would be this neighborhood. Or maybe it's it could also be a longer neighborhood. It doesn't have to match exactly with the previous n or not. So what we need to do is we need to also compute what would be the max frequency if we considered the values in between here. And the way to do that is we pick the value at n at I, and we take the value n at that position, and now we pretend that that n plus k, this is n plus k, is part of our set. So we need to compute at the boundaries. We need to compute basically also the max frequency that we would get. So when we iterate over the numbers, we don't only iterate over all the numbers in n, but also over all of the numbers n plus k and n minus k, because those are the ones where we know that we have other valid regions that we could adjust to match that value. So that is the missing part here in our initialization, and that is the only thing that we need to add as well. N plus k and n minus k. And with that, I think the solution is complete. So let's run it through the test cases down here. Make sure I didn't make any syntax errors, and it passes the test cases. Very nice. Now let's submit it to see if LeetCode accepts this solution. Right, so it passes. Very nice. Now, let's just look at the runtime and space complexity one more time. We know that we get n log n because of the sorting, and we get O of n space because of the frequency counter, and also the num targets list that we need to iterate over. And then here inside the loop, it's also O of n time. But also we do the bisect left, bisect right. That's a logarithmic time complexity for each call of that function. So even the for loop is O of n log n time. The for loop itself is O of 1 space, but since we already have n space up here, it doesn't change runtime complexity. Yeah, and with that, that's the video.